Good morning and good afternoon to everybody. Thank you for attending this second day of the TechDebt conference. Today's keynote speaker has already left his mark on software engineering. Apart from authoring several landmark publications, especially in the field of software architecture, and serving various prestigious positions in industry and academia, he has led numerous university-industry collaborations, such as the well-known Software Center partnership between 16 large European companies and 5 universities. So his perspective on what technical debt actually means for industry is indeed very pragmatic. In his blog, he recently outlined 10 rules for thriving in a digital world. The last one recommends engaging actively with our ecosystem. And I quote, "By continuously engaging with your ecosystem, you can detect the changes early on and you can identify when the time is right for you to reposition in your ecosystem." I believe that his overall work is one of the best starting points to understand what the current digital ecosystem looks like. In today's keynote, he will describe the progress and challenges on the management of technical debt in the areas of DevOps, Data Ops, and AI Ops, highlighting the need to focus on technical debt for data and machine learning, which was one of the key takeaways of yesterday's panel discussion. Please join me in welcoming electronically Professor Jan Bosch to the TechDebt conference.
Thank you so much for a wonderful introduction, Alexander. Let me start by sharing my screen. Here we are. So first of all, I would really like to thank Alexander and the other organizers for inviting me to present my keynote here at the I'm really excited because the TechDebt community is very close to my heart, and although I am not always present myself, of course, if we look at the participation by Antonio Martini and Therese Besker, who did a lot of their research with me, I am actually very passionate about the field. And what I was hoping to do with you today is to basically talk about technical debt in the age of ops. Now, and for those of you that you may know that I really like to start with a quote, and this one is a little bit more far-fetched than usual, maybe, but this is a quote by Elon Musk where he says that I think it's very important to have a feedback loop where you're constantly thinking about what you've done and how you could be doing it better. And if I think about DevOps, Data Ops, ML Ops, or AI Ops, basically what we're talking about is ways in which we can increase the speed of the feedback loops in order to make sure that we can, in much better ways, learn from what is happening in the field and what is out there. So in order to be clear on what I'm hoping to cover today, I will have takeaways that I wanted to share with you. The first is that what is important to realize is that whereas we traditionally have within the TechDebt community been focusing most traditional software development, the software which is built out of requirements, perhaps. What I see is that we are complementing, in many of the companies that I work with, we're complementing this with data-driven and artificial intelligence-driven functionality. And then if you extend the DevOps principle, you basically move from just DevOps into DevOps, Data Ops, AI, and ML Ops as the key topics to be aware of. The second, which I find very interesting, is that when you have a fast feedback loop that is enabled by these ops, you can actually start to work more quantitatively in all kinds of different factors and aspects of software development. So you do not only have to look into quantitatively measure software usage or other things, it also allows us to start to quantitatively measure the effect of efforts that we conduct in order to decrease the amount of technical debt in our system. So if we identify a technical debt item, we identify what kind of interest or cost that this is generating in the system, we invest in fixing that. We would like to then quantitatively measure that the impact that we were expecting to see from the reduction of technical debt or the refactoring of the software is actually being achieved or not. And working with the ops is something that allows us to do that. And then finally, the third point where I will be spending a bit of time on is that data-driven and AI, machine learning, deep learning functionality, I believe adds new types of technical debt that we need to address as a community. Now, what I do want to stress now here in the beginning is I do not have all the answers. What I'm mostly stating is that ask me to look a bit into the future. These are some of the things that I see happen, and I thought it was valuable and relevant to share that with you in the community as part of this keynote today. So please do not expect me to say these things. I think it is more a call to action in the community in order to make sure that we can, as much as possible, start to address these kind of topics. What I was hoping to do with you is to talk through a number of topics. First, I wanted to, for those of you that don't know me or don't know the Software Center, I was hoping to do a brief introduction so you have an idea of who I am. Then, and this is a bit of a funky sidetrack maybe for some of you, but I believe it's very important to understand what we mean with digitalization, because if I look at the Software Center that I'll present in just a minute, we see that digitalization, which we view as software, data, and AI, is really the key driver for a lot of change in these companies. And then I want to talk about some of the research in the that we conducted in the area of DevOps, some of the work that we've done in the area of data ops, and some of the work in the field of ML ops, with the intent of highlighting some of the challenges we've seen in the industry and that we expect will require research and need to be addressed in the TechDebt community as well. And finally, to give you a bit of a taste of where I've been spending my time the last few years, I wanted to share some of the AI engineering research agenda work that we've been conducting in our research group. And then we'll get to conclusions. And I'll try to wrap up in about half an hour or so, but it's 44 slides, so I'll see how far I get. First, for those of you that don't know me, I currently have professorships at Chalmers University of Technology, where I work full-time, and a part-time appointment at the Technical University of Eindhoven in the Netherlands. I also run Software Center that I will introduce in the next slide. But I haven't been an academic for all my life. Actually, I spent around 10 years in my career working in industry. I worked for several years in Nokia Research Center, running the Software and Application Technologies Lab. And I also spent time in Silicon Valley working for Intuit, a great company for those of you who are from the United States. I loved working for that company, and I was VP Engineering Process and had a few other roles there as well. In addition to Software Center and my academic research, I today also divide my time between some consulting engagements, a number of boards that I'm on, and I spend some time on angel investing. So if one of you or some of you have interest in starting a company and are looking for angel, perhaps some advice, feel free to reach out to me, and we can always discuss if this is something that is of relevance for both of us. What I think is more interesting is Software Center. Software Center is a collaboration, as Alexander already mentioned, between 16 large companies and 5 universities, and the mission of significantly accelerating the digitalization capability of the European software-intensive systems industry. And we have traditional Swedish companies such as Ericsson, Volvo Cars, AB Volvo, the truck company, and Scania, and Saab Defense. But we also have Danish companies such as Grundfos and Dive. We have German companies such as Bosch and Siemens, as well as Jeppesen, which is part of Boeing, an American company. Finnish companies like Wärtsilä. They're all members of the Software Center. And together we explore a variety of topics around digitalization. If you look at our research, we actually look into a number of topics. One is continuous integration, continuous test, continuous delivery, and DevOps. That's, I think, one big topic in which there is a lot happening. A second topic in which, for instance, Antonio Martini and Therese Besker have been very active is the continuous architecture theme. In that theme, we look at the architectural technical debt topic as well as other technical debt challenges. We have work ongoing around metrics. Miroslav Staron is one of my colleague professors who is very active in that field. We have a theme on customer data and ecosystems that is led by Helena Holmström Olsen, who's a professor of computer science at Malmö University, also very active in Software Center. And the newest theme is what we call AI engineering, which is the theme that I will come back to towards the end. And although all the companies that I showed you earlier are started their lives as metal bending companies, we do not only work with companies in the embedded system space, we also have connections to Booking.com, which originally was a Dutch startup. Many of you will have heard of Spotify, the Swedish music distribution company. Rovio is the company behind Angry Birds King, the company behind Candy Crush. Klarna is a Swedish company that provides credit for people that buy things online. And one of our former PhD students is now working at Microsoft, and some of our other PhD students have also been visiting. Some of you may have met Alexander Fabian, who is now in the data science team at Microsoft in Redmond. So that's the background of who I am. Now that gives you a bit of a feel for where this talk and the content in this talk is coming from. If we talk about digitalization, I often notice that people are not quite clear on the definitions here. So if one of my favorite definitions is the one by Gartner, which says that digitalization is the use of digital technologies to change a business model and provide new revenue and value producing opportunities. It is the process of moving to a digital business. If you look at the software center companies, as I already alluded to, many of them started their lives as metal bending companies. So they were very much on mechanics and gears and chassis and all kinds of other things. And then in the second half of the 20th century, depending on the company, electronics started to be added to the product. And this is actually true. Ericsson, for a long time, actually was owner of a steel mine, because at that point telecom switches were purely mechanical devices. There was no electronics in them. But of course, at some point in the 1960s, 70s, and sometimes 80s, electronics was introduced. After that, software was starting to be added to those systems. And in the last decade or so, maybe 15 years, data has become an increasingly important part for these companies. And the most recent technology that has been added is, of course, artificial intelligence, using machine learning and deep learning solutions in order to improve the performance of systems. When we talk about digitalization, we're actually talking about the three digital technologies on this list, meaning software, data, and artificial intelligence. And those are what we feel quite important, because it leads to a number of very important changes in the way that we think about the businesses and the companies that we have. I mean, here with the 5 technologies, and with the color we indicate whether these are becoming increasingly commoditized or whether these are representing increasingly differentiating and innovative functionality. And as we can look in the embedded system space, we see that mechanics and electronics is increasingly commoditizing, and software, to a larger extent, even data and artificial intelligence, are increasingly the differentiating technologies where the differentiating and innovative functionality resides. This isn't true in all industries. For instance, in the gaming industry, people often view software already as a commodity. It just needs to be there, and they really differentiate themselves in the data intelligence, and I think that those of you that are into computer gaming can recognize that. There are 3 important changes that I want to outline here. The first is that this transition in where is the differentiation very often leads to a change in the business model. So going from a transactional business model, you buy a car, you drive that car for a number of years until you're sick and tired of the car, and then you buy your next car. We see that many of these companies are exploring and moving towards subscription-based models, where you can either through some form of renting or subscription get basically access to, for instance, a car or to other equipment that software center companies have available. I think that already today, Volvo Car allows you to get an XC40 as a subscription, where you basically pay a fixed monthly fee, and you have a 1 month notice period. If you don't want to have the car anymore, you just cancel the subscription and the car goes back and you're free. So that's the first change that we see, the business model changes. The second is the ecosystem in which you operate changes, because every time you bring in a new technology, software, data, and AI, you also need to bring in new partners, new people that help you develop that kind of technology, which is of course, an ecosystem evolution. And then the third dimension, which is what we're going to be spending a little bit more time on in this talk, is of working. So here is where we see the whole ops culture develop. DevOps, data ops, ML ops are basically, or AI ops if you want, are some of the ops that are being presented in this context. I know that people are talking about DevSecOps and other things, so I didn't want to go to all the ops, but these are the three major ones that I believe are very important. Of course, security is also important, but that's not the focus of my talk today. Together with my colleague Helena, I put some references in the presentation. If you're interested, you can look them up. We developed a model where we basically outline what are the transitions that companies go through as they move from traditional ways of working to much more digitalized ways of working. And why this is important is because we see that as companies evolve, the types of technical debt that they struggle changing. So if we start with the business model dimension, the second one from the bottom, you see that companies move from selling products, physical products, to offering their product as a sale, as a service, as I mentioned earlier in the Volvo example. Then they moved increasingly towards complementary services around the product. For instance, if you go to AB Volvo, they have services around helping truck drivers to figure out where to buy fuel for the truck or where they can safely rest and eat. They also have services for fleet owners around SLAs and uptimes. So we can see all kinds of complementary services around the product. The next step is that you move towards monetizing based on how you help the customer improve some of its performance indicators. So rather than getting paid for the product, you help, for instance, in the telecom space, if an operator has a reduced churn, a reduced number of truck rolls, or other reduction of cost of serving customers, then you are getting a part of that value that is created by you through helping your customer. That you move towards a multi-sided ecosystem where, for instance, you collect data from your primary customer base and then you resell that data to a secondary customer base. And that leads to a product upgrade dimension, which then also looks different because initially you don't want to give any upgrades to the product. Then you move towards very reactive software updates. Then you focus on more proactive and continuous software updates. Then you move to continuous upgrades of software and of periodic upgrades of electronics and hardware, and then you move towards a fully digitalized offering. And the final one at the top, you can see where we move the AI/ML/DL connection, where we talk about data for human interpretation, moving into DevOps, moving into systems that do fully autonomous experimentation on their functionality. I think it's important to set the scene here. Sorry for taking a bit of time to talk you through this, because I believe it's important to understand that this is not the world that we're living in isn't anymore the traditional, give me a set of requirements, I build according to the specification, and then I give you the software and we're fine. And if I happen to accumulate some technical debt, we just have to go and fix it. Now, the world is much more complex than that. And that's what I will show you in the next slide as we start to look into the age of ops. Yeah, here we have what we call the holistic DevOps model. And the way that we look at it is basically that any software-intensive system will have three types of development going on in it. There will still be the traditional requirements-driven development, where you get a specification, you build the software according to the specification, and you test and you deploy. That's the first type. The second type is what we call outcome or data-driven development. That's when you develop for instance, an A/B test. Yeah, you have a certain outcome that you're looking to accomplish, and what you do is you run A/B experiments, for instance, in order to improve that outcome. So in this case, a team will not get a requirement specification, but especially in the online world, for instance, a team will get a requirement or a request that says your part of the website suddenly currently has a conversion rate of 3.2%. Our request to you is that you focus your energy on improving conversion from 3.2 to 3.4%. And then the team is entirely free to figure out how to actually move the needle on the KPI that they're asked to improve. And then finally, we talk about AI-driven development. I suppose that many of you have looked into this, but the software center companies are spending hundreds of millions of Swedish kronor a year accumulating and collecting data from their products in the field and other sources, and they basically look for ways in which they can use that data in machine learning models or deep learning models in order to accomplish functionality in their products that performs better than traditional algorithmically developed functionality. Independent of the type of development that we see ongoing, all these systems will still be subject to continuous deployment. Also, safety critical systems are moving towards continuous deployment, and all these systems will continuously behavioral data that allows us to observe whether a system is working in practice or not. So I think it's important. That is at least the development that we're seeing. And within the 16 companies in Software Center that we're talking about, some of them are further along. Companies like Ericsson, for instance, already today, for customers that want it, deploy new software in live base stations every 2 weeks if you want it. Companies like Volvo Cars are starting with A/B testing in employee cars. So these are things that are really becoming reality, not just in the online world or in the Amazons or Googles of this world. This is also becoming a reality in the embedded systems world. So what I will do now is go through the three ops, DevOps, Data Ops, and ML Ops, and talk a little bit about what it is, what we see as some of the challenges, and some of the work that we've done in that space. So if we talk about DevOps, this is an old slide. I think it goes back to 2012 or 2013. But basically what we see is that companies move through a very predictable pattern in the way that they evolve. So they start off with traditional development. Then you get the adoption of agile practices at the team level. Then you move towards continuous integration, and you see that and then you see that the verification and validation loop is being included as well. Then you move towards continuous deployment, when you get the whole DevOps thing in place. And once you have DevOps in place, you see that many are starting to use the DevOps or continuous deployment infrastructure as a mechanism for A/B testing, where you have two different versions of a feature. You give some group of your customers version A of the feature, you give some other group of customers version B of the feature, and then you measure which of these two versions is performing best in practice. For those companies that are spending a lot of time on customizing products for customers based off a platform, what we see is that the customization doesn't work well anymore once you start to adopt continuous deployment practices. And then I see many companies move towards a continuous delivery model where all software for all products in a software product line or product portfolio are generated from a single code base in a fully automated fashion. And as you can imagine, the transition from a custom-based platform approach to a configuration-based platform approach brings with it enormous amounts of technical debt challenges in the software itself, because now everything where customization takes place needs to become configurable, but also very much technical debt in the infrastructure of the system, because what is happening is that now suddenly I need to automatically derive products, I need to automatically test products, I need to identify defects and get them back. Once I deploy, I need to have monitoring and logging solutions in place that figure out if the system, new version of the software is performing as it should. And there are significant technical debt challenges once you get into this space. A benefit, going back to some of the research that I was referring to earlier, is that if you have a DevOps or continuous deployment approach in place, you can actually to be much smarter about how you build your systems. We have research that shows that for a typical system, around 1/3 to 2/3 of all the features of the system are never used or used so seldomly that the investment in the feature development was actually not justified. It was basically a waste. And we see this with several of the software center companies as well, because some of the companies in the software center, the first time a feature is activated for the first time at any customer, the company follows a specific procedure to track the activation of the feature in order to ensure that it works properly in the customer context. And several of the software center companies have actually surprisingly long lists of features that have never once been activated by a single customer that they have available. So you really want to move away from that kind of thinking. And here we see you can do that. It's called the Hypex model. You have the feature backlog. Before you implement the feature, you try to capture what is the expected behavior of this feature. If I add this feature to the system, how will the system behavior change? How will the customer behavior change? Then you build the minimal viable feature, which is the first 10-15% of the feature. You get it deployed out in the field, and you can now measure the actual behavior. What am I actually seeing in practice? And then, of course, in practice, you will hardly ever see what you were expecting, leading to a situation where you can then start to decide if you should abandon the feature, if you should extend it, if you have already accomplished what you were looking for after having built 30% of the feature and you don't have to do anything more, or you figure out that what you were doing was actually the right functionality, the wrong realization, and you have to re-implement. Now, in your mind, replay this for an architecture refactoring. Once I have a prioritization of an architecture refactoring, I believe that one of the things that we can now do in a DevOps context is to actually specify in quantitative terms what the effect of a architecture refactoring will be. And once I have described the expected effect of an architecture refactoring or of some technical refactoring, I can do the first slice of that refactoring, get it out, and start to measure if the refactoring actually had the intended effect or not. And if not, we have a very good basis to do a little bit of a deep dive into why that is not happening. And I think that DevOps gives us the opportunity to start to look into quantification of the benefits of technical debt management, refactoring aspects that I believe is not sufficiently well researched within the community so far. This kind of thinking around experimentation and learning in the context of complex systems is not a novel thing. This is by one of our PhD students, David Isamatas. So some of you may have run into him. What's important here is that we have a technique called value modeling, where we explicitly have an approach to explicitly model the value of a feature, of some functionality, or a product, and we can then associate value models with that can guide our decision making. So that's the first the DevOps I wanted to talk about. I am running a little bit late, so Alexander, I think I need until 16:40 to finish the presentation or the keynote. So the next topic I wanted to spend some time on, a bit briefer maybe, is data ops. Data ops is a little bit of a sometimes funky and not so well understood term. We have a paper on this in case you're interested. I have a reference in one of the upcoming slides. But basically what we're talking about is a methodology to design, implement, and maintain a distributed data architecture. As I see a lot of the companies that we work with, their attention is really shifting in the software development community from how do we get the features and functionality out to how do we build reliable, high quality data pipelines and infrastructures that allow us to actually keep track of how our product is performing in the field, how our customers are using our systems, etc. Data ops, of course, blends software development techniques and AI agile management principles into analytics pipelines. And the idea is that using data ops, you can actually automate a lot of the processes, and that allows you then to really shorten the time to gain insights from raw data. That's basically the thinking. Again, I'm not going to deep dive on this. If you're interested, there's a reference here at the bottom around data ops. But what we've done is defined a maturity model. This is Aishwarya Rai, one of my PhD students, as well as David, where we talk about the 5 stages that we see companies go through. If you're wondering what the A, B, C, D, etc. are, these are all the cases that we studied in the paper. And we see companies go from ad hoc data analysis to semi-automated to agile data science to continuous testing and monitoring, and then finally to full-fledged data ops. And again, if you're interested, please take a look at the material, because I think that's much more interesting to do that. Another piece of research that we conducted in this area, and I think that there's still a lot of work to be done. There's an enormous amount of technical debt in most companies in their data pipelines. And one of our approaches to address that is to develop a language for modeling data pipelines. This is work in progress. This is not fully deployed, where we basically describe in a conceptual language, a domain-specific language if you want, what the characteristics and expectations are on each element in a data pipeline. And here you basically see, starting from where the data is being generated, an initial connection node which has a number of constraints around this, because the A, F, M, and S are forms of validation that we put on the data. Then it goes into a raw data storage. The next step is that it goes into ingestion, extraction. Typically, you try to take out certain features and ignore the rest. Then you move to labeling, because you need to have labels associated with that data. Then you get to refined storage, and then you can use these things, for instance, for machine learning and deep learning modeling, model evaluation, and then model serving. So this is a data pipeline approach, but I believe that we would benefit as a community from much more research around what are the technical debt items and topics around data pipelines or data management in general that companies experience. One of our other papers, also by Aizvaria, is where we look into some of the data management challenges. I don't want to talk through all of these in the interest of time, because I'm starting to run late. But we have identified lots of challenges. This is in a number of different cases, where we talk about things like debt items around data storage, difficulty due to the heterogeneity of data, dependencies in data that really shouldn't be there, different debt around data extraction methods, etc., etc. With one of the postdocs that recently left our group in order to move back to Finland, Lucy Vakatara, we worked on automatic data validation approaches, which I think is an interesting way to think about this, because what we were basically trying to figure out is, how can I have a holistic framework for fully automated data validation that is not just constrained to cells in the data or rows, or to full data sets or cross data sets or on data, but it's basically an approach that allows you to do all those things within one framework. So we run tests and have mitigation strategies at the cell level, at the feature level, data set level, and at the feature and data set level, or at the data stream level, where you, for instance, can have things that if in one data stream you should have a certain statistical distribution over a time window, and in another data stream, the statistical distribution should be similar. When those two start to shift apart, to talk about a very advanced form of data validation, we can, within this framework, detect those kinds of changes. Other ones is that even within a data set, if over a time window we see that the median starts to shift, or the statistical distribution starts to shift, or we're starting to see more and more empty cells or empty rows, that is an indication that things are going wrong, and we can then take mitigation strategies or sound alarms. So I think that that's a quite interesting piece of work. The last part where I wanted to spend a bit of time before we go to the AI research agenda and the conclusions is machine ML ops, basically. And why do I care so much about ML ops in this context? Well, I think that many of you have seen a paper that is now already 6 years old, actually, by a number of people from Google, which was published in NIPS. It's now called NeurIPS. Where they talk about the hidden technical debt in machine learning systems. And what they identify there is that the little black box in the middle is the machine learning code, but all the other boxes around it need to be in place in order to have an industry strength production quality deployment of those machine learning models. And what we see is that many people are actually or are not spending much time on this. And if we look at the traditional simplified machine learning model. What you have is you first have to get the data, so assemble the data set, then you create a model, you train and evaluate the model, you may then tweak or move towards a different model. So the inner loop is really concerned with finding the optimal and training and evaluating it to get to the satisfactory accuracy or F1 score or whatever you want to use. Once you have a model that you're satisfied with, you can move to deployment. But since we live in the age of DevOps and DataOps and MLOps, of course, I do not deploy once. I actually have a continuous process where I'm constantly trying to improve the model, maybe retrain the model with the most recent data, etc., etc. If you look at where the discussion is in the machine learning community, as well as in the software engineering community, to be honest, everyone and their brother is talking about creating models and training and evaluating. But if we look at where the energy and time and effort goes in the companies that we work with, we see that getting high quality data in place and deploying it in a way that is production quality and is properly monitored and supervised, and alarms get raised when things go wrong, that is the hard part. It is not about the models and the training and evaluation. And I think it's important to realize that as a technical debt community, because the technical debt will not be so much in the middle two boxes, but it will be on the data side, at the front end, to assemble the data set, and it will be at the deployment side where things actually go live into the field. And I think that that's important to realize and to look at that. We recently worked with Menu, who is a PhD student at Malmö University, one of the universities in Software Center, on a MLOps framework where we distinguish between the data pipeline, the modeling pipeline, and the release pipeline. I don't want to spend more time on this, but if you are interested, then you can reach out to me and we can see if we can get you a copy of the paper when we get it accepted. This is all fine and dandy, but the challenge is that with companies show that there's actually quite a few challenges out there. Together with people from Peltarion, the company I'm on the board of, Anders, Björn, and Luca, we did a study into what are the software engineering challenges of deep learning, not specifically on technical debt, but there are several technical debt items here. So you can already see one of the items there being glue code and supporting systems. Now, that's a typical example of where there is a lot of accumulated technical debt. Dependency management is another one where we see a lot of challenges. Monitoring and logging is often very rickety. A lot of baling wire, chewing gum, and duct tape in order to make things happen, but not a lot of very systematic engineering in that context. So that paper gives you an indication. It's already a few years old now, but gives you an indication of what we have identified a few years ago. Another paper, again by Lucy and us, is about the different challenges in different maturity levels. Again, this is too much text, so I will not talk you through this. Another interesting paper that was published last year in Information and Software Technology, or IST, paper where Lucy is the first author, where we, based on a literature review, looked at all the papers that look into large-scale machine learning systems that have actually been deployed in real-world industrial settings, and what are the challenges that they are identifying. You can see a little bit of a table here where we can see that unstable data dependencies and data quality problems is a clear technical debt topic. Difficult feature engineering is one of the other ones that I think we would be. Serving skew is a technical debt around the data. Balancing efficiency and effectiveness in an ML workflow is, I think, an interesting one. One of the other ones is limited interoperability and explainability. Again, I think that there are items that need to be addressed there. Last point, and then I will start to wrap up. What we see is that a lot of people work on experimentation and prototyping, but when you start to become more mature, when you start to actually deploy in a non-critical or critical or cascading fashion, or you move towards autonomous machine learning and deep learning, AI engineering, a topic that we are now spending a lot of time on, is becoming increasingly important. And what we've done, you can find the reference in the bottom here, is we've developed a research agenda where we identified what are the key challenges that we see around AI engineering that need to be addressed. And over the years, we've built up a team with David looking into autonomously improving systems, Yuchi looking into A/B testing, Iris from Siemens looking into how do I take operational data and get strategic data out of it. Aizvaria looks into data versioning and dependency management. Lucy looks into monitoring and logging. Taylor into automatic labeling. Hugo into heterogeneous hardware. Menu into design methods and processes for machine learning systems. And Hong-Yi is looking into federated learning, and he's now recently started to look into reinforcement learning as well. So these are some of the topics that we believe are quite important, and there's quite a bit of technical debt in each of these areas to be studied and addressed as well. Now, with that, I want to jump to conclusions because I'm already overdue from what I had promised Alexander I would finish up in. But it's George Colony famously said that in the future, all companies will be software companies. I think you got it almost right. I believe that in the future, all companies will be digital companies using software, data, and artificial intelligence. And as a TechDebt community, we need to really take that into account. So what we see is it's no longer traditional software. Data-driven functionality, AI-driven functionality becomes increasingly important. That gives us the DevOps, DataOps, and MLOps. The fast feedback loop in ops allows us to quantify and measure the effect of efforts to reduce technical debt. So I challenge you to quantitatively predict the benefits of refactorings and then measure that your prediction is actually accurate in the systems that you work with. And then finally, I believe that there is a host of opportunity in data-driven and AI ML/DL functionality in terms of new types of technical debt that we really need to start addressing as a community. And with that, if you want to learn more, I have a number of smaller or larger books that you can either get from me in PDF form for the middle two ones. You can buy on Amazon, or you can get hold of in different ways. If you're interested, just reach out to me. And with that, I would like to thank you for your attention. If you're interested, I write a weekly blog post on LinkedIn. Alexander's already alluding to that. You can also find it on my own website. And of course, I'm on Twitter and on Medium. And with that, I would like to thank the organizers of TechDebt this year once again for inviting me, and I would be very happy if I could answer a number of questions. So, Alexander, back to you.
Thank you very much, Jan, for the great keynote. As I said in the beginning, you offered a really pragmatic perspective on what our environment really looks like in the AI era. So now we have a very interesting question by Justus in the chat. A question on measuring the impact of architectural refactorings in DevOps and potentially rolling back if measurements aren't acceptable. This sounds feasible for performance or scalability, for example, but I would imagine that the benefits of refactorings targeting maintainability, evolvability, would slowly manifest over weeks or even months. Do you think that such an approach is still feasible for large refactorings? Would a rollback after months really be realistic?
Yeah, so I think that's an excellent question. First, I think that for those of you that haven't looked into A/B testing, many tend to think that I can deploy something, I have the A/B test, and within a few days or a few hours, I have answers on whether there is an effect from the B alternative, which is often the treatment, or not. So I think that's, and I will stop sharing my screen because then people can see us. Maybe that's a better approach. So I think that is a little bit too simplistic. Even especially in large online companies, there are A/B experiments that run for months at end because the signal that they're measuring or the frequency at which certain things occur is so low that you need the long calendar time in order to measure the effect. And I think that in this case, we are in a similar situation when it comes to predicting and measuring the reduction in, for instance, maintenance costs for certain types of features. I'm not saying it's perfect, but what I'm concerned with is that our research shows that companies very often get the impact of features wrong. And I predict that we get the expected impact of many refactorings actually wrong. And so I think that it's not a matter of, is this hard to measure? Because of course it's hard to measure, but I think it is about how do we start to reason about developing a feedback loop between the impact of a refactoring and what we can measure in whatever form. Because I believe, based on my general experience in software development, that probably we're wrong in at least half the cases of what the impact of a refactoring actually turns out to be in practice. So,
thank you. Caroline is also excited about the keynote. She's having problems getting her head around new types of technical debt related to data. Do you have any examples?
Yeah, so one of the biggest ones is that the data quality is something that most companies in Software Central are really, really struggling with. Let me use a concrete example. What we see is that in one of the companies that we work with, we see that over time, different teams become dependent on data generated by another team. That other team is not aware of the first team being dependent on the data that they generate, because they think that they're the only ones consuming the data that they generate. And as a consequence, they may randomly change whenever whenever they feel the need to change the format in which they generate the data. And break these kind of connections in the system. And then you can say, but this is not technical, that is more of a process issue. No, but what we have been doing is we've been developing software solutions that allow you to detect these kind of things. We're looking into how you can automatically mitigate, for instance, if a data field suddenly has or a data frame suddenly has an additional field added to it, you can still get the original data out of it, so the team that was dependent on this data can continue to use it and then use that over time to change its own software so things don't break. But especially in these kind of dependencies in data pipelines, there are lots and lots of examples of technical debt, and I hope that helps.
Thank you. I think we have time for another question by Abdallah. Excellent keynote. The question is how we can measure the impact of refactoring in the ops, taking into consideration that refactoring's impact is usually invisible from users. I think he's referring to the A/B testing that you mentioned.
Yeah, and I think it's an interesting question. So the impact doesn't have to be visible to users. It should be visible to the company that is conducting the Now, and what we know is that quite a few technical debt refactoring items are concerned with reducing future maintenance costs or improving the mean time between failures or other quality issues. But specifically for maintainability, no, the user of the system will not be able to see this, but within the company, if we can show that for every item on the backlog, due to refactorings, the average time for conducting things that are roughly similar in size is starting to decrease, which means that it becomes easier to maintain the system. Those are the types of analyses that we can most certainly run on data, I believe.
Very quick question by Marion. Do you have experience with data catalog techniques? Can they help optimize data in data pipelines? We have 30 seconds, so I don't know if it's sufficient.
Yeah, so I think that's a question that we have to take offline. And if it was Marion, you said?
It was Marion. Yeah.
Yeah, so, and I would be happy to put her in touch with Aishwari, who is the PhD student that is looking into this, because Aishwari has been looking in detail into some of these things. 9 seconds, Alexander. So you better
Thank you so much for the excellent keynote. Thank you so much.
Thank you for inviting me. I really appreciate it.